Okay, so problem 4 from the examples. And I am going to have to go as quickly as I can to give you guys as much time as possible on the exploration. But problem 4 gave you this equation. And so, of course, the first 2 steps that we're going to do will be the simplifying step. And this time we are actually going to locate holes. So this will be one of our new behaviors for this problem. So we start trying to simplify. The x minus 1 is already in factored form, but the quadratic next to it does factor. It factors as x plus 3, x minus 2, and the quadratic in the denominator also factors. It factors as x minus 2, x minus 4. And so what that means is that the x minus 2's are going to cancel. So this is the first time that we are actually able to truly simplify an equation. And so our simplified equation has these 2 factors left in the numerator, and it has this factor left in the denominator. Okay? Now, because of this x minus 2 that canceled, we are actually going to have a hole in our graph this time. Now remember, a hole is a hollow circle. It's a hollow dot. And so that means it's got to have an x-coordinate and a y-coordinate to it. We know the x-coordinate to the hole because it's where this vertical asymptote would have been. So this x minus 2 right here would have given us a vertical asymptote at 2, and so that gives us the x value for our hole. And the analogy that I made with my classes last year is that a vertical asymptote is a cut in the graph, and when you're able to cancel that vertical asymptote out of the equation, you're able to remove the cut. And what it leaves behind is it leaves behind a scar on your graph. So your graphs the way it normally would, just like any other cut. If you heal a cut on your skin goes back to looking the way that it did before, but there's a little mark left behind on your skin. And so our graph, for the most part, is going to look like a normal graph. It's going to look like this equation's graph, but that graph is going to have a scar or a hole left on it. So we know where the x value for that scar is. In order to find the y value for that scar, we take our x value and we plug it into our now simplified equation. And so I'm going to go ahead and plug in the 2. And so, of course, 2 minus 1 is just 1. 2 plus 3 is 5. And 2 minus 4 is negative 2. And so our hole occurs at negative 2.5. Okay? So we've got our simplified equation. That's the one we're going to use for all of our SHRATEY steps. And now we know where we're going to put a hole on our graph. Okay? So then the next thing is to actually begin the analysis process. Just remember, now we are doing the analysis process with our simplified equation. And so our simplified equation has an x minus 1 on top, an x plus 3 on top, and an x minus 4 on bottom. Okay? So now, the R step. This part and the A step are the same as they have been with the other problems. I'm going to take the numerator here and set it equal to 0. And so each factor gives me a solution. And so x equals 1 is going to be a solution. X equals negative 3 is going to be a solution. So these are my 2 x-intercepts. Then I take my denominator and set it equal to 0. And so x equals 4 is my vertical asymptote. And this was what you guys learned last year is called a non-removable discontinuity, because it's part of the denominator that we could not get rid of. We could not remove. Okay, so there's our vertical asymptote. Okay, so continuing our analysis, once again, still with our simplified equation, x minus 1, x plus 3 over x minus 4. We have no t behavior. None of those factors in our simplified equation are squared. So no t behavior in this graph. And now our e behavior is the next one that's brand new. Remember that e behavior is based off of leading term over leading term. And the leading term in the numerator, if we were to FOIL it out, would be an x squared. And the leading term on bottom is the x. This is the first time this is a top-heavy equation. So if we look at the actual SHRATEY handout, so pull that out, here's our end behavior, right? And we are now in this category, the top-heavy category. And so what I want you to notice is we're going to have, number one, we're going to have an oblique asymptote. And oblique simply means angled. So it's going to be at a slant. Okay? And it tells you kind of what that means. It says that the ends of our graph are going to look like one of these functions. It's going to look like y equals x or y equals x squared on the ends. But in order to figure out what it's going to look like, you have to follow this hint. And it says you may need to use division. You're going to use division. So you can cross out the word may. If you are top heavy, you are going to use division to find the equation for your oblique asymptote. So what I'm going to do is I'm going to go back, and in order to do the division with this equation right here, I actually do have to FOIL out the numerator. So the numerator would FOIL out to become x squared plus 2x minus 3. Okay? And I'm trying to divide it by x minus 4. So I'm going to actually have to do the division. Now, how you do the division is up to you. You guys were taught two kinds of division. You were taught polynomial long division, and you were taught synthetic division. Now, obviously, the synthetic division is the shorter method, so if you remember it, that's the route we would normally go. So normally what we would do is this. If we're dividing by x minus 4, we're going to put a positive 4 in the box in the upper left corner of our synthetic division. And we are dividing it into 1x squared plus 2x minus 3. And we leave an empty row, and we carry the 1 down. And now we begin the synthetic division rotation steps. So step 1 is to multiply diagonally. So that means that I'm going to multiply this 1 times the 4. And I'm going to take that product and write it up at a diagonal as well. So I put the 4 there, and then I add down. So I get a 6. Next, I take the 6 and multiply it times the 4. So I get 24. And when I add down, I get 21. And you may remember from last year that this right here is your remainder. And when you're looking for the end behavior graph, the remainder doesn't matter. Now once again, theoretically, as we move into the next section, by the end of the week, you'll better understand why it is that the remainder doesn't matter. You'll better understand what it is that the end behavior is calculating. But for right now, we are simply practicing the mechanics of this. So what this synthetic division is telling us is that this right here is the equation for our oblique asymptote. So we abbreviated OA, oblique asymptote. And what this equation right here is telling me is it's saying my equation is y equals this 1 right here tells me that there's a 1x, and this 6 right here tells me there's a plus 6. So this right here is our end behavior asymptote. So we're actually going to graph the line y equals x plus 6 as a dashed line. Okay? And so now we are actually able to sketch after we find our y-intercept. Okay, so the last step is the same last step, same process, no new anythings here. We're going to plug 0 in for x. And once again, we still plug it into the simplified equation. And when we plug it into the simplified equation, we get 3/4 as our answer. So, now we can start sketching. So, 1, 2, 3, 6. I'm going to mark that with a 6. Okay. And so now we can actually start putting our pieces of information on our graph. So we know we're going to have a hole at 2, negative 2.5. So that would be right about there. We know that we have 2 x-intercepts. We have one at positive 1. And we have one at negative 3. We know we have a vertical asymptote at x equals 4. So 1, 2, 3, 4. And we know that we have y-intercept at 3/4, which is kind of hard to do with this stylus, but right around there. And we know we have an oblique asymptote at y equals x plus 6, which has a y-intercept of 6 and a slope of 1, so it would look like this. And now we actually have enough to sketch our graph. Okay, so this left branch over here, this section over here to the left of the vertical asymptote, I already know 4 points technically on that branch. And so I have more than enough to sketch this branch's curve. I'm going to go through all 4 of those points. I'm going to curve to follow the oblique asymptote. I'm going to make sure not to fill in that hole accidentally when I try to draw through it. And I'm going to curve to follow the vertical asymptote. So there's the left branch. Now what ends up happening with this other branch to the right of the vertical asymptote is it virtually always ends up being up off of your graph. And since we're not doing tables of values and drawing super precise graphs here, we're just sketching, you're probably not going to get much of that on here. So what you would do is this: you would just sketch a branch that goes between the 2 asymptotes as far up as you can up towards the top and be done with it. I mean, once again, the completed notes that I'm going to post online will actually have a small table of values that show you where that point actually is. But we're not trying to be super precise here. We're just trying to sketch these functions to serve a larger purpose later on in the unit. Okay, So now you guys need to go ahead and move into the exploration, and the ones you're graphing in the exploration are much simpler, and remember we are just sketching. Okay, so we'll get everybody on the same page and make sure you guys don't have any questions tomorrow and wrap things up with this exploration tomorrow. Thanks. Bye.